Welcome back to the deep dive. We are really glad you're here. Today, we are pivoting a little.
A little, yeah.
Usually, when we look at drug development, the big question, the burning question is always, does this thing actually work?
Right. The efficacy question, the million-dollar question, as they say.
Exactly. But today, we're asking a darker question, and, arguably a much higher stakes one.
Which is?
Will this drug, while it's curing your headache, accidentally stop your heart?
It sounds a bit like a movie trailer voiceover. But in our world, that's literally the job. That's safety pharmacology.
Specifically, we're tackling the ICH S7B guideline. And for all you students listening, maybe you've got boards coming up or a regulatory exam.
We're just trying to survive a pharmacology module.
Yeah, exactly. This is the document that stands between a routine prescription and, well, a fatal arrhythmia.
It's the ultimate safety net. And to be really precise, we're diving into the document titled The Non-Clinical Evaluation of the Potential for Delayed Ventricular Repolarization, QT Interval Prolongation, by Human Pharmaceuticals.
That is a title only a regulator could love.
It just rolls right off the tongue, doesn't it? It
Yeah.
hit step 4 back in May 2005, and, it's been the gold standard ever since.
So here's our mission today. We are not just going to read you the rules. Anyone can download the PDF for that.
Right.
We want to reverse engineer the logic behind the rules. We want to get at the mechanism of the heart so that when S7B asks for a very specific test, you understand why it's asking.
I love that. We're moving from just memorization to real intuition.
Yeah.
If you get the physiology, the guideline just becomes, common sense.
Okay, so let's start with the boogeyman. We hear QT prolongation all the time in those drug ads. Side effects may include. But what does that actually mean for a patient? We're not just talking about a line on a graph being a millimeter too long.
No, not at all. The clinical endpoint we are absolutely terrified of is a specific chaotic type of arrhythmia called torsade de pointe.
Twisting of the points.
Exactly. It's French. And if you see an ECG of it, the signal literally looks like a twisted ribbon spinning around an axis. It's this rapid, disorganized heart rhythm.
Okay, and that causes what? Fainting?
It can cause fainting, seizures, yeah.
Yeah.
But the real danger, the whole reason we have this guideline, is that it can degenerate into ventricular fibrillation.
Which is basically instant cardiac arrest.
It is. The heart stops pumping blood and just sort of quivers. If you don't shock it back into rhythm immediately, that's it. Game over. So S7B exists to predict the risk of that very specific event before a drug ever touches a human.
That sets the stakes perfectly. So to understand how we predict it, we have to go back to what, first year med school physiology?
Pretty much. Back to the cardiac action potential, the heart cell itself.
I always use the camera flash analogy for this. You know the old disposable ones?
Yeah, I remember those.
You press the button, you get the flash, that's the heart beating. But then right after, you hear that high-pitched whine. That ee.
The capacitor recharging.
Exactly. And you can't take another picture until that whine stops. That whole process, that's what we're talking about, right?
That is a surprisingly accurate model.
So the QT interval in this analogy is the total time from the flash going off until that battery is fully recharged and ready for the next shot.
Yes. In electrical terms, the flash is depolarization. That's sodium rushing in, triggering the squeeze. And the recharging is repolarization, resetting the cell so it can fire again.
And this S7B guideline is just obsessed with that recharging phase.
Totally obsessed.
Oh.
Specifically with delayed ventricular repolarization. If that recharge takes too long, if the battery wind drags on, the heart becomes electrically unstable. It creates a vulnerable window.
Where a stray signal can cause big
A
problems.
huge problem. It can trigger that torsade de pointes we just talked about.
Okay, let's zoom in then. We're looking at that action potential graph. You've got the 5 phases, 0 through 4. S7B really only cares about one of them.
It focuses, heavily on phase 3.
Okay, so set the scene for phase 3.
So just picture the wave. Phase 0 is that sharp spike up sodium rushing in.
Right.
Phase 2 is the plateau where calcium is kind of holding the contraction. And then phase 3 is the rapid downstroke. This is the big reset. And the key player here is potassium.
Potassium leaving the cell.
Correct. To reset that negative charge inside the cell, you have to dump positive ions out. So potassium rushes out to bring the voltage back down.
And the heart has specific doors for these ions. It's not just a free-for-all.
Well, it's a whole system of channels. But for S7B, there is one current that matters more than any other, and you need to know this one. It's the S-dol.
The rapidly activating delayed rectifier potassium current.
Just remember, it's the main driver of repolarization in humans. If you block ICH-Bell, you block the exit door.
Yeah.
Potassium gets stuck inside. The cell stays positive for longer.
The QT interval stretches out and you're in the danger zone.
You are squarely in the danger zone.
And this brings us to the gene. The one with the really funny name that always shows up on the exam.
The hERG.
hERG.
Human ether-a-go-go related gene.
Okay, I have to ask. Why ether-a-go-go? It sounds like a nightclub from the 60s.
It basically is. It comes from fruit fly genetics back then. Scientists found a mutation where if you anesthetize the flies with ether, their legs would start shaking rhythmically.
Like they were dancing at a go-go club.
Exactly.
Scientists really need to get out more.
They do. But the important thing is that the human version of that gene, hERG, is what encodes the protein that makes the pore for that hERG channel.
Okay, let me connect the dots for everyone listening. A company makes a new drug. That drug molecule happens to be the perfect shape to get stuck in that hERG pore.
Like a cork in a wine bottle.
It plugs the hole, potassium can't get out. Phase 3 gets delayed, the QT interval gets longer, and the patient can go into cardiac arrest.
That is the exact causal chain. And S7B is the instruction manual for finding that cork before it ever leaves the lab.
Okay, before we get to the testing, I want to try something to help our listeners remember this. I've been working on a mnemonic for the action potential phases, just for S7B.
Oh, let's hear it. I'm all for it.
All right, so picture the numbers on the graph. Phase 0. 0, it sounds like the letter O. So O is for open. Sodium gates open.
Okay.
Phase 2. 2 rhymes with glue. That's the plateau phase, where calcium and potassium are kind of glued together in balance.
Glue. I like that.
And then the most important one, phase 3. 3 rhymes with free.
Free. Oh.
Potassium breaks free. It exits the cell. This is the S7B danger zone. And finally, phase 4. 4 rhymes with floor. You're back at the resting potential floor.
3 is free. That is brilliant. If you can just remember that phase 3 is potassium breaking free to reset the heart, you understand why blocking it is so dangerous. That's a great tool for an exam.
Okay, so we have the mechanism. We know the villain is a drug blocking the hERG channel. How do we catch it? The guideline talks about an integrated risk assessment.
Right. And integrated is the key word. It's not one single test. It's a strategy. And that strategy has 2 main pillars. A non-clinical strategy combines an in vitro assay and an in vivo assay.
So test tube and animal.
Basically, yeah. Component 1 is the ICH assay. This is pretty much always the hERG assay. You take cells, usually HK293 cells or CHO cells.
Wait, HK293, aren't those kidney cells?
They are human embryonic kidney cells. And because they don't have their own noise from other heart currents, they're the perfect blank slate. You genetically engineer them to express only the hERG channel.
So you've made a cell that's basically just a container for that one specific potassium door.
Exactly. Then you can clamp onto it, measure the electrical current, and just drip your drug on it. If the current drops, your drug is plugged in the hole. Simple as that.
So it's a yes-no on the capability. Can this drug block the channel?
Precisely. It's highly sensitive. It catches almost everything, but it's almost too sensitive. It's happening in a dish. There's no liver, no proteins, no nervous system. It's pure mechanics.
Which is why we need component 2, the in vivo QT assay.
The live animal study. Here we aren't measuring a single current. We are looking at the actual ECG in a living, breathing creature.
This feels much more real. But isn't it kind of redundant? If the hERG test is positive, why even bother with the animal?
Because biology is messy. Just because a drug can block the channel doesn't mean it will in a living body.
Yeah.
Maybe it binds to proteins in the blood and never even reaches the heart.
Or the liver just chews it up instantly.
That happens. Or, and this is really interesting, maybe the drug affects other channels that actually cancel out the bad effect.
Oh, like a multi-channel blocker.
Yes, exactly. Some drugs block the bad potassium channel, but they might also block a calcium channel. Blocking calcium actually shortens the action potential, so the 2 effects can cancel each other out. The hERG test would be screaming, danger, but the animal test would say, nope, we're all good.
Wow. So the hERG test is the smoke detector, but the animal test is the firefighter actually checking to see if there's a fire.
That's a perfect way to put it. And usually, this animal test isn't a separate experiment. It's integrated into the S7A safety pharmacology core battery. You'll have an animal with a little telemetry implant measuring its ECG while it just walks around its cage.
Okay, listeners, this is an important point. If you're taking an exam on S7B, there is a trap waiting for you right here. It's all about species selection.
The classic trap, yes.
You're designing your study. You need an animal. You pick a rat. Why did you just fail the exam?
You failed because the rat heart is fundamentally different from a human heart when it comes to repolarization.
But we use rats for everything, for toxicology. Why not this?
Because, remember how we said humans use the I current for phase 3? Rats don't. Rats mostly use a different current called I current, transient outward current. Their repolarization is like lightning fast.
So if I give a rat a drug that completely blocks hERG...
The rat won't even blink. Its heart doesn't care about that channel.
Huh.
So you'll get a false negative.
Yeah.
You'll think your drug is safe, and then you'll give it to a human and have a catastrophe.
So no rats, no mice.
Never use rodents for the S7B repolarization assessment. You have to use a species that shares the I mechanism with us. The standard is the dog, usually a beagle, or a non-human primate, like a cynomolgus monkey.
Are there smaller options? I mean, dogs are expensive.
You can use guinea pigs or rabbits. Interestingly, guinea pigs do use Icanova unlike their rat cousins. But for the big regulatory submission, it's usually the telemetry dog or monkey.
Got it. No rats, dog or monkey. Okay, now let's talk about the other big headache in these studies, the math.
Ah, yes, the heart rate correction.
We know the QT interval isn't a fixed number. It changes all the time.
It has to. I mean, think about it. If your heart rate goes up, say you start running, the beats are getting closer together. If the QT interval, that recharge time, stayed the same, the next beat would try to fire before the last one was done recharging.
Which would be chaos.
Absolute chaos. So just as a rule of physiology, when heart rate goes up, the QT interval must go down. They're inversely related.
So here's the problem for the drug tester. I give a drug. The dog's heart rate drops because, I don't know, the drug makes it sleepy. The QT interval gets longer. Is that because the drug blocked the hERG channel? Or is it just because the heart slowed down?
And that is the confounding factor. You have to be able to strip away the effective heart rate to see the drug's true effect on the channels.
And that's where the formulas come in. Bizet and Friedericia.
The two names you will see constantly, they're just mathematical formulas that take the raw QT and the heart rate and spit out a standardized number, the QTC, the corrected QT.
It sort of normalizes everything to 60 beats per minute, right?
Roughly, yeah.
Oh.
It lets you compare a QT at 100 beats per minute with a QT at 60 beats per minute on a level playing field.
Is one better than the other? I always see Bizet used in the clinic.
Bizet is the old standard, but it's actually not great for these animal studies. It tends to overcorrect at high heart rates. So a dog with a fast heart rate might look like it has a problem on Bizet's formula when it really doesn't.
And Friedericia.
Friedericia uses a cube root function. It's generally seen as more accurate for the heart rates we see in dogs and monkeys. The guideline doesn't force you to pick one, but it does say you need to justify your choice.
So trust the QTC, but always check the math.
And always look at the raw data, too. If the QTC is screaming danger, but the raw QT barely budged, you've got to question your formula.
Let's circle back to something we touched on with the in vitro versus in vivo debate, metabolites.
Yes, this is a big one.
Yeah.
And it's a great example of why you can't just rely on the animal study either, which is kind of paradoxical.
Wait, I thought the animal was the ultimate safety net.
It is, but think about this scenario. You give a drug to a human. Humans have different liver enzymes than dogs, so maybe the human liver breaks that drug down into something we'll call metabolite X. And maybe metabolite X is a super potent hERG blocker.
But the dog doesn't make metabolite X.
Exactly. Or the cell line in the dish doesn't make it. So you have to know your metabolism. If a drug has a major human metabolite, S7B says you'd better test that metabolite specifically. You might have to synthesize it and pour it directly on the hERG cells.
It's really like detective work. You're looking for the killer, but the killer might be a ghost that only shows up inside a human liver.
That is why the guideline keeps hammering on integrated risk assessment. It's not a checklist, it's a dossier. You're compiling evidence from the dish, from the dog, from metabolism data, from the chemical structure. You're building a case.
And speaking of chemical structure, that's another big hint the guideline gives us, right? Chemical class.
Absolutely. History repeats itself. You're developing, say, a new antihistamine. You should be sweating.
Because of terfenadine, Seldane.
Yeah, exactly. It was a blockbuster drug in the 90s that caused QT prolongation and sudden death. It's basically the reason this guideline exists. So if your new molecule looks like an antihistamine or an antipsychotic class is known for this issue, you need to test extra hard.
Okay, we've covered a huge amount of ground here. Let's condense it. For the listener who just needs that cheat sheet for their exam, the 5 things to tattoo on their brain.
Okay, let's drill the S7B 5 pillars.
Pillar number 1.
The target. S7B is all about preventing delayed ventricular repolarization. The mechanism is almost always the inhibition of the hERG current through the hERG channel.
hERG, got it. Pillar number 2.
The strategy. It's an integrated risk assessment. You need both in vitro data to check the channel blocking potential AD and Vivo data to check the physiological reality. One is not enough.
Pillar number 3. The big trap.
The species rule. No rats or mice for the QT assessment. Their heart currents are wrong. You must use dogs, monkeys, ferrets, or guinea pigs.
Pillar number 4.
The correction. You cannot interpret QT data without correcting for heart rate. You have to calculate the QTC using a formula like Bizet or preferably Fredericia.
And finally, pillar number 5.
The context. S7B doesn't exist in a vacuum. It works alongside ICH S7A. In fact, the in vivo QT data is often collected during the S7A core battery cardiovascular study. It's about reducing animal usage.
If you can explain those 5 points, you've pretty much mastered the document.
I would say you know it better than 90% of the people working in the industry.
I do have one final question. We've talked about how rigorous this all is. We've got cells, dogs, complex math. Does this mean that if a drug passes S7B, it's 100% safe?
No.
Yeah.
And that's the humility of science, right? S7B reduces risk. It doesn't eliminate it. And there's a specific blind spot the guideline itself acknowledges.
You mean the simulated pathological conditions?
Yes. Think about it. In all these S7B tests, we're using healthy, young, well-fed beagle dogs. Who actually takes the drug in the real world?
Your grandma, who has heart failure, diabetes, and is already on 5 other medications.
Exactly. A healthy heart has what we call a repolarization reserve. It can take a hit and keep on ticking. A sick heart might already be standing on the edge of a cliff. A tiny bit of hERG block from a so-called safe drug might be enough to push it over.
So the guideline is sort of hinting that we need better models of sick hearts.
It's the frontier of safety pharmacology. How do we model a diabetic ischemic heart in a regulatory test? We're not there yet. But for the listeners, the future scientists, that is the problem that's waiting for you to solve.
I love that. The guideline isn't the finish line, it's just the current best practice.
Absolutely.
Well, there you have it, the ICH S7B. It's not just paperwork. It's the difference between a cure and a cardiac arrest. To everyone listening, good luck with that exam.
You've got this.
Don't just memorize the rules. Understand the rhythm. Thanks for listening to The Deep Dive. We'll catch you next time.